Hello, and welcome to this demonstration of GNSS data processing in PPP mode with the help of the GNSS software. We will first give a general introduction to the software, then we will see how to run it and analyze the solutions, and finally, we will present some direct applications as examples. GNSS is an orbit determination and precise positioning software developed by the cres for more than 50 years. It can process all types of geodetic observations and measurements, such as those from VLBI systems between quasars and pairs of stations, SLR systems on LEO and MEO satellites, LORRI systems on LEO satellites, and GNSS systems between radio navigation satellites and receivers on Earth or on board LEO satellites. This multi-technical ability has made GNSS very successful. Nowadays, it is used by numerous research laboratories for a wide variety of objectives and purposes. GNSS can solve and estimate a wide variety of geodetic parameters. To do so, the algorithm compares the actual measurements with a model that has been implemented into the software. Take as example a GNSS signal that is emitted by a satellite, passes through the atmosphere, and is received by a receiver on ground. At the start of the processing, the distance between the satellite and the receiver is different from the distance calculated by GNSS, because, for example, the position of the receiver and the impact of the atmosphere on the measurement are not accurately known. Each new observation provides information, and it is the accumulation of measurements that ultimately makes it possible to solve the system of equations and find an optimal solution for the parameters that we want to estimate. However, it is necessary that the number of measurements is greater than the number of unknowns that we want to solve for. To approximate the solution of overdetermined systems, such as these ones, GNSS uses the least squares method. The use of the GNSS software requires a computer connection between the user and the server of the GET laboratory in Toulouse. First, the user transfers the Linux measurement file as well as the director file containing the processing parameters via the SSH protocol to the GET server. The additional required data are extracted from the GET database and are combined in a program called prepar, which creates a single file called FIC. This file is then transferred via again the SSH to the user's PC running the GNSS program. At the end of the processing, several files are generated. The solution file that contains the estimated coordinates of the GNSS receiver, the listing file which makes it possible to analyze how the processing went, and the statistical file that contains useful data to analyze more in detail the processing in question. Processing GNSS data with GNSS requires several steps. To make it easier for the users, the command execppp has been developed. Consequently, one just have to use the command in question, specifying the name of the Linux file that we want to process. This will, first of all, create the director file defining the processing parameters. Second of all, create the receiver characteristics file containing its a priori coordinates and the type of antenna and receiver. Third of all, it will retrieve from the database all the information that the processor requires, such as precise satellite orbits or clocks that will serve as a priori data. Fourth of all, it will preprocess the Linux file to detect cycle jumps, short passages, bar stations, etc. And finally, the execution of the GNSS program will take place. When the treatment is finished, the solution can be plotted. The PPP technique allows to determine precisely the position of a GNSS receiver, regardless of any other receiver. It is of course in the user's interest to use the greatest number of satellites and the most precise orbit and clock products. The classic source of these products is the International GNSS Service. The GET database provides GNSS users with various EGS orbit and clock products, including those from the cres CLS Analysis Center called GRG products. GRG products have a distinctive feature of being directly compatible with GNSS for PPP processing, having used undifferenced phase measurements to fix the ambiguities to integer values, which improves the accuracy of the solution radically. To illustrate the advantages of combining data from several GNSS systems and resolving the ambiguities of phase measurements, we will compare different coordinate solutions of a geodetic station. The station is stationary, but its coordinates have been estimated every 5 minutes for 7 days. A perfect solution would give the same value all the time. However, there are several sources of error, such as the distribution of visible satellites from the station, the precision of the orbit and clock products used as a priori, or errors in modeling the effects that the atmosphere has on GNSS measurements. The calculation of the standard deviation of the series of solutions makes it possible to quantify such errors. Let's see how it differs now, depending on whether we process a single GNSS system at once or we do a multi-GNSS analysis. Figure number 1 shows the coordinate time series obtained using data from the GPS system only. The computation of the standard deviation yields 6.4 millimeters in this case. A similar calculation, only using data from the Galileo system, gives a slightly greater standard deviation of 7.1 millimeters, as seen in figure number 2. This is because the Galileo system does not have as many satellites as the GPS system as of today. Nevertheless, the combined processing of GPS and Galileo measurements yields a better standard deviation of 4.6 millimeters, which is significantly lower than that of the previous independent solutions. When the integer ambiguities of the GPS and Galileo phase measurements are resolved to integer values, the solution is further improved with a standard deviation of 3.1 millimeters. Let's now see how the different types of processing can be run by using the exappp command. At least the following 3 arguments must be used as inputs to execute the command. -rin specifies the RINEX file to process. Compressed or uncompressed RINEX2 or RINEX3 files are accepted. The following argument is used to characterize the dynamics of the receiver. -static indicates that a single set of receiver coordinates will be calculated from all the measurements found in the RINEX file. This is the option used for fixed receivers. -static-Kalman estimates at every measurement epoch the coordinates of a receiver undergoing small displacements, that is, less than a few meters, such as those during an earthquake or landslide. -Sinem calculates the coordinates of a mobile receiver at every epoch independently. Finally, the const argument allows both to specify the constellations to use and whether or not to fix the ambiguities. Now, to specify the constellations, we just have to follow the international convention that identifies them with a letter. The letter G for GPS, the letter R for GLONASS, and the letter E for Galileo. To indicate whether we want to resolve the ambiguities or not, we will use a different case. Lowercase letters for floating ambiguities and uppercase letters for integer ambiguities. Note that fixing ambiguities in GLONASS phase measurements is not yet possible. To process data from several constellations simultaneously, one just needs to combine the corresponding letters accordingly. To obtain some hands-on training through tutorials on PPP processing with the GENS software, several practical exercises are offered. We just have to go to the GenTP directory to see a list of practical exercises. Let's begin with TP-PPP. The TP-PPP directory contains an instruction manual TP-PPP, with line-by-line helpful comments. This directory also contains the RINEX files of the IPGT, USUD, and YAR stations. The objective of this exercise is to show the 3 types of PPP processing through these 3 exappp command lines. The static case, which estimates a set of coordinates based on a day of data from the geodetic station. The static Kalman case, which computes 1 position per second for 1 hour of the USUD geodetic station undergoing an earthquake. Finally, the Sinem case, which computes 1 position per second of the IPGG oceanographic buoy while undergoing tides. We invite you to use the contents of the TP-PPP directory to test the installation of GENS on your PC and have a first overview of the exappp command. At the end of a PPP treatment, it is key to validate the processing before moving on to the interpretation of the solution. To do so, we must analyze the listing file created by GENS in the directory gens-listen. The command listen summarize is very useful as it allows to extract from the listing the most significant information and indicators. For example, the Bilan line contains information regarding the GNSS constellations that have been processed, the dates of the start and the end of the processing, the number of satellites encountered, the number of passages, and the number of detected cycle jumps. There is also information concerning the Earth deformation corrections that have been applied, such as solid tides, ocean loadings, atmospheric loadings, and polar tides. The range and phase residuals at the first iteration and when convergence is achieved, as well as the number of measurements processed and discarded are all essential information that can also be found by using listing summarize. The solution file is also produced by GINS and can be found by default in the GIN batch solution directory. As its name suggests, it contains the result with the GNSS receiver coordinates. If we look over the solution file, we will notice that it contains a header with information regarding the processing features and the solution expressed according to three different projections. XYZ Sol expresses the solution in the Cartesian coordinate system. FLH Sol corresponds to the geographical coordinates. ENU Sol expresses the solution in the local east-north vertical coordinate system. To plot the solution file or any other file produced or outputted by GINS after the execution of PPP, there is a very useful command named plot cres PPP. This command allows to visualize as a plot the following files: a solution file or a list of solution files, a statistical file, the GINS listing, the prepare listings, and the Linux file. The instruction to use this command can be seen by typing directly plot cres PPP. Here's an example of plot cres PPP with solution file as input. In this case, the ENU local coordinates option has been used. These three figures represent the variations in the position of the receiver as a function of time in the three directions: east-west, north-south, and vertical. Likewise, but using this time GINS listing file, the pass option allows to view the passages of the different satellites as a function of time for each constellation. The SATS option shows the number of satellites that are visible by the receiver for every epoch. With a statistical file, it is possible to trace the passages of the satellites in a local coordinate system center on the receiver with the AE option. We also have the possibility to analyze the residuals of GNSS measurements as a function of time or as a function of the elevation of the satellite. To do so, we have to use the ERR option, which also allows us to identify a set of suspicious data, in this case colored in blue. To sum up, with these three commands, that is PPP, list and summarize, and plot cres PPP, it is possible to process the data, make a diagnosis of the processing, and plot the solutions. The different practical tools that we have shown will let the users get their hands on GINS for the first time and eventually be ready to process their own data. By way of illustration, the TP Relax exercise will allow us to compute the co- and post-seismic displacement of the Con station located in Concepcion, Chile, where the very violent earthquake took place in 2010. This practical work will also teach us how to process several Linux files covering the period of the earthquake. If we run it, we will see that the Con station moved 3 meters to the east at the time of the earthquake and continued moving due to the post-seismic relaxation that happened for several months after the earthquake in question. This last example is a study that we have conducted by processing the data from 1,300 stations of the GeoNet network in Japan. The data from these stations were processed independently in PPP mode with GINS, and the coordinates were estimated every second. This animation shows the deformation of the Tohoku region, as well as the propagation of seismic waves during the 2011 earthquake in Japan. This demonstration of the GINS software tool is now complete. Join us in the virtual classroom if you have any questions. If you are interested in this software or if you would like further information, do not hesitate to send us an email. Thank you and cheers.